Good evening, everyone. Welcome to the Special Functions and Number Theory seminar. So today's speaker is Professor Hussein Mourtada from University of Paris, Diderot, and he'll be talking on integer partitions, monomial ideals, and hypergraphs. So Professor Mourtada, I just wanted to say that there are many people here who have come to listen to your lecture. I'm just showing it. We are meeting in a seminar hall. So
Thanks a lot. I'm very happy actually to be
okay,
with
over to you, sir.
with you and to speak in your seminar. Also, especially that it is based in India. I've never been in India, but I'm very happy also to be soon in India. I was very much inspired by Ramanujan's work, and especially that I came to Ramanujan's work from my domain, which is singularity theory and algebraic geometry and things like this. But today I will not tell you very much about how I came to partitions and partition identity. Today I'm happy to tell. To give a talk which is, in principle, it should be very basic. I forgot the title that I gave, but it was something like maybe integer partitions. Atul just said it, integer partitions, monomial ideals, and graphs or hypergraphs. Okay, but at the heart of this work is Rogers Ramanujan identities that you probably know much better than me, but let me please recall them, because also I will write them differently. They will be the same, but written. So one can write them of the following way. So there are two identities, one which can be 1 plus sum for k larger or equal to 1 to q to the power q squared over 1 minus q times etc. times 1 minus q to the power k. And this is equal to the product for j larger or equal to 1, j congruent to 0 plus or minus 2 modulo 5 of 1 minus q to the power j, and all of it divided by the product for j larger or equal to 1 of 1 minus qj. Okay, and if you have seen these identities before, then you know that the natural way is to write them as product 1 over product for j congruent to 1 or 4 modulo 5 of 1 over 1 minus qi. So it's a bit strange to write them this way. But as I said in the abstract, I'm going to show some identities which are in some sense dual, in some sense that I hope will be clear after my talk, and it will be related more to this, to the numerator. So this is one identity, and the other identity, it looks like this: 1 plus sum for k larger or equal to 1 of q to the power k2 plus k divided by 1 minus q times etc. times 1. Yeah.
Yeah. So in the first
Yeah,
identity, you mean q to the power k square?
absolutely. Thank you very much. And here it is k squared plus k. And this is equal to the product for J larger or equal to 2, J congruent to 0 or plus or 1 modulo 5 of 1 minus q to the power j, and all of it, sorry, all of it, so the equality is here somehow, all of it is divided by product of for j larger or equal to 2 of 1 minus q to the power j. And the other way of writing it, let me please write the partition version. So so these are Rogers-Ramanujan identities, the Q-series identities, but which will be very important also for me is the partition version of these identities. It said that if we take I belongs to 1 or 2, so we take n a positive integer, so non-zero. Then let me call Tin to be the set of partitions whose parts is whose parts are without equal parts. Let me say it like this: without equal parts. Nor consecutive parts. And this is, or the other one, I will call it, let epsilon I n be, well, I wasn't precise here. So there is, and the part 1 appears at most I minus 1 times. In particular, for I equal 1, there is no, the part 1 doesn't appear. Okay. And I will consider epsilon I of n to be the number of, I call it, well, this is not the number really, this is the set of partitions whose parts parts are congruent to plus or minus 2 plus I modulo 5. I hope I'm not making any mistake, because I usually write it for I equal 1 and for I equal 2 not together. So it says that the number of parts, the number of partitions of type T, I, is equal to the number of partitions. So this is the number of partitions of type 1. So without consecutive part nor equal part is equal to the number of partition epsilon in. Okay. So this I is just to put the two identities in the same. So now, if you allow me, I will introduce, as I said, my first goal is to state let's say, two partition identities which are dual to these identities. Okay, so I will define some partitions which will appear a bit strange, but as I will hope I can show you later, they are very natural if we look from some point of view that I will precise. So these partitions, I will call them neighborly partitions. So what are neighborly partitions? So let us define neighborly. Neighborly. I never write neighborly correctly. Neighborly partitions. Okay. Again, I have this for I equal 1 to 2. It was better maybe if I have chosen I equal 1 or 2 and I equal 2 especially and continued, but still I will keep to the two cases. I will consider the two cases. Okay, so, and for a positive integer n, we call a neighborly partition or we call, let's say, we the set nin of neighborly partitions, lambda of n is the lambda of n is the set of partitions which satisfy the following. One, that for every part lambda j of lambda, there exists a positive integer, so L belongs to n strictly positive. In France, 0 is a natural number, so that's why I put this, which such that L is not equal to j, but L not equal to j, and such that lambda L minus lambda j equals 1. Okay, so which means that there is always either for any part that we consider, there is either a part which is equal to it or a part which is consecutive to it. Okay, as if we are looking to something which is the opposite of the partitions which appears in Rogers-Zamenhof identities, and the multiplicity of any part of lambda is at most 2. Okay, so we don't have parts which are repeated more than 2 times, and well, it's written a bit strangely, but let's write for every L in n, lambda L is larger or equal to 3 minus I. So it means that for I equal 1, there is no part equal to 1. 1 is not a part of lambda. Okay. So as I said, these neighborly partitions are, in some sense, opposite to the partitions which appears on one side of the Rogers-Ramanujan identities, because here we have consecutive and we have equal, or I mean, we have either consecutive or equal. And the term neighborly appears natural, because for every part you have a part which is equal to it, or which is very neighbor, which is consecutive. So it's very neighbor to it. So for instance, example, if we consider the partitions of 4, so 4 is equal to 4 is equal to 3 plus 1 is equal to 2 plus 2. This is equal to 2 plus 1 plus 1, and is equal to 1 plus 1 plus 1 plus 1. And that, let's assume that I is equal to 2. This means that we allow the partition to have 1 as a part, so we can consider the neighbor partition for I equal to of 4. These are this one is not neighborly, because you see 3, for instance, has no neighbors. This one is good. 2 plus 2 is good. 2 plus 1 plus 1 is also good. Okay, because 2 has a neighbor, which is 1. And of course, 1 has 2 neighbors. All of them anyway have neighbors. This one is not good, because 1 is repeated more than 2 times. Okay, and we allowed it to be repeated only twice. Okay, and one can see that n1 of 4 is equal just to 2 plus 2. Okay, because this one here I intervene. So this is to express the identity. It's not only a question of what kind of partitions we are considering. It's also related to some notion of signature. Okay, so we want to define a signature of a neighborly partition. The name appeared natural, but well, it can be called something else as a function of neighborly partition, but we called it signature. So for that, we will associate a graph with a neighborly partition, with a neighborly partition. Partition lambda. We associate a graph G lambda as follows. So the vertices the set of vertices of G lambda is in bijection with the parts of lambda, and we give them name. So let's say that if H is a part of lambda of multiplicity 1, so it appears only one time, then we call this vertex, x h, okay? Sorry, x h, okay? This vertex we call the vertex associated, well, maybe I write it like this, we call the vertex associated with h, xh, okay? And if h is a part of lambda of multiplicity 2, this means that to every part we have a vertex. So if it is of multiplicity 2, we call one vertex xh, and the other vertex, which is because there are two vertices then associated to h, because we have two h parts, two parts which are equal to h, and we call the one vertex xh and the other one yh, okay? And then so I divided the vertices, the set of vertices, and then if I consider the edges of G lambda, they are of the form x h plus 1 xh, okay, or xl yl. Whenever I have all of these for all the xl, xl plus 1, and yl in V of G lambda. Okay, so I join the consecutive x's, and if I have xl and yl, then I join them. Okay, so for instance, if we consider G2, let's take the 2 plus 1, 1. We have seen it here, this one. So 2 plus 1, 1. The vertices are, we have x1, we have y1, right? Because we have two, the multiplicity of 1 is 2, and we have the vertex, the only vertex associated with 2 is x2. Okay, we don't have y2 because 2 appears only once. And we join then x1, y1, and x2, x1, x2, okay? Or imagine that I take another one. For instance, let us take the partition 5 plus 5 plus 3 plus 2 plus 2 plus 1. So I think that this is also a neighborly partition, I hope. So the graph will be something like this. So we have only one x1, sorry, only one 1. So we associate with it one vertex. Here we have 2, 2. So we have two vertices, x2 and y2, that we join them together. And then x2 is joined with x3. And it will be non-connected because x5 will be joined to y5. Okay, so this graph is, the non-connected graph is G5 plus 5 plus 3 plus 2 plus 2 plus 1. Okay, and this is the graph of G of 2 plus 1 plus 1. Okay, and there is a notion for graphs. When you consider a subgraph, there is a notion of vertex spanning, which means that it has all the vertices. So a subgraph of H is, or a subgraph H of G lambda is said to be vertex spanning if V of H is equal to V of G lambda. Okay. And it's said to be, maybe I can say also that you can imagine what does it mean that it doesn't have isolated vertices. This means that you don't have vertex which are not connected with an edge to any other vertex. Okay, so we will see, this means, because we will be interested in those which without, in the graphs which do not have isolated vertices. Okay. And this allows us to define this signature. So let us the definition of signature of a neighborly partition Okay. So is how we take lambda. Let lambda be a neighborly partition. Let me write it like this. Neighborly partition. The signature of lambda, or that I will call delta of lambda, is by definition equal to sum over H, where H are all the vertex spanning subgraphs of G lambda, which have no isolated vertices. Okay. So this is then sum of H, which are vertex spanning subgraphs of G lambda, which are also without isolated vertices. Of -1 to the power the cardinal of EH, so the number of edges in H. Okay, let us look also at an example. So if I consider, let us consider an easy example, otherwise it may be long. So we consider, for instance, 2. Let us consider the neighborly partition 2 plus 2 plus 1 plus 1. Okay, so this is 5. No, this is not 5. This is 6. And the associated graph is given by x2, y2. I prefer this x1, y1, and here I put x2, y2. Okay. So if we try to see the subgraphs which have the subgraphs which are vertex spanning and without isolated singularities, then we have 2 subgraphs. Here we have, this is, it is vertex spanning, so it has to have 2, all the vertices. So x1, y1, x2, y2. And then we I cannot take, for instance, this subgraph, because then y1 and y2 will be isolated. Neither this one, because this will be y1 will be isolated. So the only there are two subgraphs. There is the graph itself, okay, which is something like this then, and this is the other graph, okay. So here we can say that delta of 2 plus 1 plus 1 plus 2 plus 2 plus 1 plus 1 is equal to, for this graph, we will have minus 1 to the power the number of edges, which is 2, plus for this graph, it is minus 1 to the power the number of edges, 3, which is equal then to 0. Okay, so this is an example of the computation of the signature, and this maybe allows to me to take this theorem. So this theorem was proved with my old student Zahra Mohsen, and so we proved that for I belongs to 1, 2, we have that sum for lambda belongs to ni of delta lambda q to the power lambda, sorry, q to the power lambda. So this is lambda means the weight of the partition, and that this is equal to the product of for g larger or equal to 3 minus I and g congruent to 0 plus or minus I modulo 5 of 1 minus q to the power g. Okay. So if we go back to the beginning of the talk, let us just see that this guy here, it should be very much like the numerator that appears here. Okay. So this to just feel this maybe another way to write it, because we cannot give an example to show that this works, is to say it is to this is equivalent, or maybe I can write corollary. One corollary, this an equivalent way of stating it is to consider for I equal to 1, 2, we can consider Ri of n to be the set of partitions of n whose parts are larger than 3 minus I, okay, which means that for I equal 1, we do not have the part 1 appearing, which are distinct. So the parts are distinct and congruent 2, 0, plus or minus I, modulo 5. Okay. Then one way of, so this is not the corollary, maybe I can say the definition of RIN, definition of this guy here. Okay. And the corollary, which is equivalent actually to the theorem that I stated above, that we have that sum for lambda belongs to NIN of delta lambda is equal to sum of for lambda belongs to RIN of minus 1 to the power the size of lambda. Okay. And in one can see that this is for a given n. Okay, for n belongs to n, we have such an inequality. One can see, of course, that on the right-hand side, this is the coefficient of q to the power n here, of this one, of this series. The coefficient of q to the power n is this term here. This is, if I call this as star, this is the coefficient of q to the power n in star. Okay. So let us look, I mean, just for fun. It has been a while that I wrote this paper, so I always, when I look at these examples, find them very funny. So, for instance, if we take n equal 6 and I equal 2. So we can see that the neighborly partitions n2 of 6, they are equal to, the set of neighborly partitions of this 6, here we allow 1. This tells us that we allow the part 1. These are 3 plus 3, 3 plus 2 plus 1, 2 plus 2 plus 1 plus 1. Okay. Of course, the graph of this one is like this, x3, y3. So the signature is minus 1 to the power the number of edge. There is no vertex spanning subgraphs without isolated singularities. So this is one delta of 3 plus 3 is equal to minus 1. This one also doesn't have, it's 3. So we have, we can write it like this, x1, x2, x3, x1, x2, x3. And it doesn't have also a vertex spanning. So we have the delta of 3 plus 2 plus 1 is equal to minus 1. The number of edges here is 2. There are 2 edges. So minus 1 square, which is equal to 1. And the delta of this one is 0. Okay. So the signature of this one is 0. We have, this is what we have computed here. Okay. So delta of 2 plus 2 plus 1 plus 1 is equal to 0. Okay. So if I take this sum here is equal 0. This sum here is equal to 0. Okay. And one also can see that in this case, that if we take R2 of 6, it's empty. There is no there's no partitions of 6 in R2. So this tells us that also this part is 0. So this is a verification on one example. So now maybe I will, of course, later we have generalized these two identities to also give some identities which we call this, we don't know if this is if it justified enough, but we call these identities as dual to Rogers-Ramanujan identities. Not only because of what I just said, but also because of the proof, because the proof in a sense that I don't know if I will be able to explain all of it, but it uses Rogers-Ramanujan identities, but also it says that these are equivalent to Rogers-Ramanujan identities. And with Puni Afsharijou, who was another student of mine, we have generalized this to give some dual identities to Andrews Gordon identities. These are very famous identities which generalize the Rogers-Ramanujan identities. Let me give you an idea of the proof, because this is quite simple. So to do this, quite simple. Well, maybe if you are used to the object that I will use. First, what I will try to do is to express this, let's see, this part here. I will try to express it. So sum of, for lambda belongs to an I, to of delta lambda q to the power lambda, like this. I would like to express it as as a generating series, or in terms, express it in terms. It's not as in terms of a generating a series which counts the subgraph of an infinite or infinite, I forgot, of an infinite simple graph. So graph which is simple, graph that we call GI infinity. Okay, so let us first do this. So we define a graph, which is the graph, the following graph. So GI infinity, maybe I can just draw it. GI infinity is the following graph. So we have, let us assume that I equal 2, okay, which means that, so let I write here G2 infinity, it will be X1, Y1. Otherwise, there will be, I will erase this edge and its vertices. Here I will have X2, y2, and here I will have x3, y3, and so on. Okay, and it goes till infinity. Okay. So this graph will be important for us, but independently, we can define something which is called the generating series of a natural object, a generating series which counts the subgraphs in the following, the subgraph of a graph in the following way. So let us define this generating series. So we take G to be, let G be a simple graph. G is a simple graph. And we consider V of G to be, let us write it this way. So this is G, VG J for J belongs to some I. Okay, so I is the index of vertices. Okay, this is the set of vertices. Then the, let us not give it a name, but we consider this S, G, V. V means all the vertices of Z, SGVZ. So this is a series which has, where there is as much variable as there is vertices, plus another variable that we will call Z, okay? And then we will take sum over all the finite subgraphs, okay? Let me write VH. So we have a monomial which is associated to this subgraph. This is a square-free monomial times Z to the power E of H. Sorry, the cardinal, I mean, of the of E of H, which means that V of H is what first? V of H is equal to the product for I belonging to I belonging to the vertices of H of VI. Okay, so this is a monomial where all the VI appears. Okay. So for instance, in our case, we can take the subgraphs. Let me take a subgraph. Let's take this subgraph. Okay, I didn't say what subgraphs I will consider. Of course, I will consider I mean subgraphs without isolated singularities. Okay. So if I take this subgraph, then the associated monomial is x1, y1, x2, y2 also. Okay. So this is what we consider. And then one can prove the following fact, which is not difficult to prove. I lost the black color. So we can see that, let's fact, it's a lemma actually, but it's very easy to prove that for I belongs to 1, 2, okay? If we consider S GI infinity of VZ, okay? So this means it will be S GI infinity of V. Here are the xi's and all the xi's and all the yi's. I write like this, okay? Y, Z, okay? So X like this is all the xi's. I larger or equal to probably something like 3 minus I. Sorry, J. okay, and y equal yj, the same thing. So this is the subgraphs, which are, I mean, the generating series counting the subgraphs, interesting subgraphs, those that we want. And then one can see that I can take a weighted version of this, or a kind of specialization. So I let me call SIW, okay, SIW of Q Z to be equal to, is obtained, let's say, is obtained from Xi by, no, is obtained by substituting Xi and Y, or Xj and Yj by Q to the power J in SGI infinity X, Y, Z. Okay, so if we call it like this, then we can prove that sum, what we want, which is sum for lambda belongs to Ni of delta of lambda Q to the lambda is equal to SI W of Q minus 1. Okay. Why is this? Maybe so this is the fact. So here I defined something, and the fact is this, really. This is the fact, okay? Why this is a fact? Because as you can see, any graph which is associated with a neighborly partition, so let's say a neighborly graph, is a subgraph of this one, okay? So if we gather all the, but there are also subgraphs which are not associated with neighborly partitions, but these subgraphs can be seen as subgraphs of a graph associated with a neighborly partition. Okay, so we have that every G lambda can be included in G infinity. Let me forget for a moment just the I. And if we have some subgraph without isolated vertices, so H, which are varying here. So those one, we can gather them together. And what's happening here is that we have G lambda correspond, let's say, we take an example, I don't know, if we take G lambda is this one, X1, lambda is equal to 1, 1, 2, 2. Okay, so this is G lambda, sorry, and so lambda is 2 plus 2 plus 1 plus 1. Okay, so what happened is that we are associating with G lambda the monomial, which is x2, y2, x1, y1, right? So after replacing x2 by q to the square and y2 by 2 to the square, what we obtain at the end is q to the power 6. Okay. So this gives will give a coefficient in q to the power 6. But also the subgraphs will give a coefficient for all the subgraphs which has vertices exactly equal to 1, 1 and 2, 2, 2. I mean x1, let us write it like this, x1, y1, x2, y2. They will also give a coefficient to q to the power 6. But they will give this coefficient either 1 or -1, because this 1 or -1 depends on the part with which is associated with z. Okay, so if h has a odd number of edges, then this coefficient will be -1 and so on. So what we see, if in this sum we gather all the edges whose vertices are exactly the vertices of, so v of h equal v of g lambda, then we see that I just remarked that I'm very late. So I'm sorry. I made a, but maybe we started a bit late. So right, Atul, maybe did we start a bit late? I have still 5 minutes, or
Yes.
how? Okay. Sorry, I'm proving something which is very simple and not relevant. Still okay. So I wanted to keep the so in this part we have explained, let's say, is interpreted this series here in terms of generating series of in terms of a generating series of counting some subgraphs of some infinite graph. Okay. Then what I wanted to say is that this there is something called now edge ideal. So we can consider the ring. We can consider the ring where with g lambda. Okay, with the vertices of g lambda, we can consider a ring. So this is k of xi. Let us assume that I equals 1. I equal 1 is a good one, or no, I equal 2. Yeah, so k of xi yi for I larger or equal to 2. Okay. And we can consider what one call edge ideal, which means that the so this is the graph. Okay, so the edge ideal is generated by whenever we have an edge, we associate a monomial with it. So here we have the monomials x1, y1, x1, x2, x2, y2. Okay, so we associate with it or this with g lambda, we associate this ring here. Okay, and we can prove actually. I don't know. It's a good idea to write exactly the, but there is a relation between the Hilbert series of this ring. Okay, so to talk about Hilbert series, I need to define a grading, and this grading is given by giving xi the weight I and by giving yi the weight I. Okay, so this gives a grading, and what we will see that this guy then can be written as some sum, if we call it A, G. Then we can write it as sum of AI, and that these AI, they have dimension over K, which is finite, and the Hilbert series is given by sum of the dimension over K of AI Q to the power I. Okay, I will tell you later why this is, we want to understand this, but there is a relation between the Hilbert series of this ring and this object here. Okay, let us not express more this relation, but then there is also the fact that this ideal here doesn't come from nowhere. This ideal, the one written here, is a kind of polarization of the ideal which is given by x1 squared, x1, x2, x2 squared, and so on, x2, x3, and so on, which is seen in K of x1, x2, and so on. Okay, so there is this polarization which also allows us to found a relation between the Hilbert series of this guy, let me write it, of K of x1 till x2, quotient by this ideal here, by x1 squared, x1, x2, x2 squared, x2, x3, and so on. Okay? And so there is a relation between the Hilbert series of this and the Hilbert series of this one here. Okay? And as we said, there is also a relation between the Hilbert series of this one with the S, what we call it SI, let us write anything, WQ. And then we proved before maybe something like this. And then we proved before that this is related with this one. Okay, so now we arrived to this, to look at this thing here, and I must tell you that if we call this B, the ideal B, and we are interested in B L or Bn, Bn is actually generated by the monomial. So here again, I'm giving to x1 the weight 1, the x2 the weight 2, and so on. That Bn is generated by the monomials xj1 times etc. times xjk, okay, such that j1 plus etc. plus jk is equal to n, okay? So this means that the monomials Bn is generated, okay, generated. But also this, so these are exactly in, as you have remarked, in correspondence with partition of n, okay? But also we would like to be in this quotient. So we would like not to be zero in this quotient. Not to be zero in this quotient means that our monomial here can't be divided by x1 squared or x1, x2 or x2 squared and so on. And if you think really 30 seconds or maybe 2 minutes, you will see that this means exactly that the partitions that we are considering here are the partitions which appears in Rogers-Ramanujan identities, which means without consecutive part nor equal part, okay? So going then from the statement of Rogers-Ramanujan identities, using it and using the three let's say, paths that I told you about, going from Hilbert series of this one to the Hilbert series of this one, and then to the generating series, and then from the generating series to the counting of the neighborly partitions, we arrive to prove the two dual identities. These are two identities which are dual to the Rogers Ramanujan identities. Something important that I should say is that these identities are equivalent. So we ask the question whether it is possible to use these identities to prove, to make the other way to go from the identities about neighborly partitions to prove the identities, Rogers-Ramanujan identities. And this was recently done by Kathleen O'Hara and Dennis Stanton in the case of Rogers-Ramanujan identity, but I think that it's an interesting problem also for Gordon's identity, and this is seems to be an open problem. Sorry, Atul, I see that I'm very late. Yeah, sorry. I'm late for my course because I give a course after in some. No, I still have.
Thank you very much, Professor Mourtada, for an interesting talk connecting these Rogers-Ramanujan type identities to Hilbert series and graphs, this hypergraphs. Are there any questions? So I had one question. So you already said that you have a dual to Andrews-Gordon identities. Is there a corresponding dual to Bressu identities, which are for even moduli? Andrews-Gordon would be for odd moduli. Or
I didn't think about it. So it's very interesting to try to.
Yes, sorry.
Yeah. So it would be a very nice thing that because I met already Bressu identities, but now I forgot about them. So it would be very nice to try to see if one can prove something which is. It's not clear in my mind actually, because it might be not. I mean, there should be maybe a dual, but I'm not sure that this. Let's say instrument that we are constructing here will work also for Bressu identities. For some technical things that I would like to discuss with you, maybe probably in India.
Okay, thank you. Yeah, any other questions?
Can I ask a question?
If not, let's thank Professor Mourtada.
Gaurav want to add questions.
Yeah.
Sorry, Gaurav. Yeah, please.
So
thank you very much.
I'll maybe send you email. That's fine.
Okay. Thanks a lot. Thank you very much for inviting me. And I am not used to really to. I decided that sometimes that I'm not